Okay, so this is section 2.7, chemical nomenclature. I guess I was supposed to cover chemical compounds in the last one, but it snuck onto this page. But it is actually important to talk about when we're talking about naming. There are two types of compounds, molecular compounds and ionic compounds. So again, ionic versus covalent. That's N, covalent. And covalent are molecular. They're held together by covalent bonds. So these are molecular compounds. And it's really simple. Ionic compounds contain metals, or a metal and a nonmetal. And then covalent compounds are all nonmetal. Again, the metals are on the left-hand side of the staircase, and the nonmetals are in the upper right of the staircase, or the upper right of the periodic table. And we're going to walk through all of that before. You're probably not going to see it. You should be able to recognize it, but we're probably not going to walk through it in class until next time. So ionic and molecular. When it comes to chemical nomenclature, there's two things that we need to look out for. There's the two things that we need to look out for are, do we have a binary compound, which means basically just two elements, or tertiary or more. So a binary compound has two elements and that's it. Any binary compound is always going to start off the same way. So regardless of what system, because we're going to go through a bunch of different systems and it's going to feel overwhelming. Regardless of what system, if it's just two elements, you always start the same way. The first element, the element on the left, keeps its name. And then the second one, the element prefix plus an IDE ending. Okay, so as an example, if I see MgO, right away I'm writing magnesium, leaving some space, oxide. Okay, and then I go back to my thing and I say, all right, is magnesium have anything special? Is it a non-metal, or is oxide any special? Is there a special thing there? So there's a couple of like rules, but always it's going to start with that base. First one always keeps its name. Second one, again, this is binary. The second one gets the IDE ending onto the prefix. Okay, all right. So let's do chemical nomenclature. Chemical nomenclature. Compounds containing only monatomic ion. So ultimately, this is binary. Your book does it this way, but it doesn't really, bothers me a little bit. So only monatomic ions, essentially you've got two things together. It's going to contain, it will always contain a metal and a non-metal. Okay, so a metal and a non-metal for our first binary. So if it contains non-metals, you're going to do a different naming system. So first thing you want to recognize is, does it have a metal? The metal should come first if it's done properly. So you're going to see the metal ion first. So very simply, the ionic compounds from 1 through 3A, okay, so we'll talk about groups too, zinc and silver are always going to be in this category. We're going to talk about why zinc and silver and cadmium, actually, I should add that as well. Cadmium 2+, cadmium always comes as 2+. Essentially, if they always have the same charge, there's no reason to put anything other than zinc or cadmium. So by saying zinc, I'm already telling you it is a 2+ charge. So adding anything after it doesn't help. So simple ionic compounds. The first written, the positive ion always gets written first. Again, this is going to be the metal. And it keeps its ordinary elemental name. So that's the thing that I just said. The first one always keeps its name. The negative ion, you combine the root with the IDE ending to get what you need. So let's just do this first example here. CaBr. C is calcium. Ca is calcium. And Br is bromine. But of course, we're going to get rid of the ending ine and put in bromide. Calcium bromide, done. That one's finished. So do the next one. All right. What is the formula for lithium nitride? And this is where we're going to start talking. We're going to need charges to do it, but lithium has a +1 charge, nitrogen has a 3- charge, and Li3N. I need 3 lithiums in order to overcome the 1 nitrogen I have. So together, the total charges from all of the lithium, I have lithium plus, lithium plus, lithium plus. Together, that gives me +3. And then the 1 nitrogen, which gives me a total of -3. Together, that is neutral. So that's the idea behind that one. All right. So that is naming things. And actually, why don't we just do this one while we're here? Al2S3. So pause it and come up with the name. Aluminum. Oh, guys, just misspelled that, didn't I? You just got to roll right through it. Otherwise, you're going to mess it up. Aluminum sulfide. Aluminum sulfide. Okay. Again, because Al is in group 3A, we're good. We're just going to call it aluminum. Don't need to do anything else. All right, perfect. So binary compounds, again, first one keeps its name, full name, next one gets an IDE ending. Anything that contains polyatomics, again, those polyatomics are the groups of atoms that are always groups of atoms. So there's at the end of this page, you're going to see, or at the end of this set of notes, you're going to see that table again. So if there is only 1 ion, okay, you are always going to call that is going to get the ATE ending. So as an example, PO4 3-, that's the only polyatomic containing oxygen or oxoanion that contains phosphorus. So this one is called phosphate. Again, there's the ATE ending. CO3 2- is the only carbon containing oxoanion or polyatomic. So what do we call this? Carbon 8. So the weird thing here is phosphorus is what you want to call it, but we truncate some of that and say phosphate. Carbonate, we don't call it carbate, we call it carbonate. So we just write it all out because we were used to it and that's what it sounds like. So some of this is just convention. So although I'm going to give you a rule, generally you have to get used to what the root actually is. So the root for carbon is carbonate, weirdly enough, okay? When there are 2 possible ions, okay, the one with more oxygens gets the ATE ending and the one with fewer gets the ITE ending. So we have SO4 2- and SO3 2-. Well, the SO4 2- has 1 more oxygen, okay? So the fact that it has more oxygens means it's going to get the ATE ending. We're going to call this sulfate, and the one with fewer oxygens, sulfite. Okay, sulfate and sulfite. So pause me now and decide what the names of the NO3- and NO2-, those are the only 2 polyatomics with nitrogen. NO3- is going to be nitrate, and NO2- is nitrite. Again, 2 options, 8, and then ite is the next option. I should point out the fact that all of these are lowercase, including the stuff that I've done so far. No uppercase, they're not proper nouns. Carbon should be lowercase, sulfur, all of those prefixes should be, everything should be lowercase. Next up, when there's more than 2 ions, you kind of just have to get used to it a little bit. So in this case, we have ClO3, ClO2, so basically 4, 3, 2, and 0, or 1 oxygen, okay? Well, I can tell you that ClO3- is the chlorate, and ClO2- is chlorite. So we start there, chlorate and chlorite. And then one with an additional oxygen, we're going to call perchlorate. And the one with 1 fewer is hypochlorite. Okay, per and hippo, more and less the prefixes that we need. So this is the maximum you're going to see. Chlorine is one. You should memorize, you should know these because these are ones that you're going to see pretty regularly. Chlorate, chlorite, hypochlorite. Okay, so again, if you know chlorate and chlorite are in the middle, chlorate being 3, then you know perchlorate and hypochlorite. As long as you know the endings of those, you know which one belongs at the top and which one belongs at the bottom. All right, good. So one more annoying thing that we have to get used to is hydrogen is often an addition to some of these. So yeah, so we're looking just at naming these things. We haven't actually put them in any full names yet. We're just looking at the names of these individual polyatomics. You can memorize them, but you got to understand there is a systematic way that this started and not necessarily continued. So the new modern way is anytime you see hydrogen, you're just going to say hydrogen. Okay, so I'm going to use the first one here, HCO3. So the base ion is CO3 2 minus. Okay, so we know that the CO3 2 minus is carbonate. Okay, so HCO3 2 minus. So if I combine an H plus and CO3 2 minus, I'm left with my HCO3 minus. So now I've added hydrogen there. I can't call this carbonate because carbonate is taken up by the CO3 2 minus without the hydrogen. So we need to call this something. So the modern new way of saying this is the way that you should know is hydrogen carbonate. Unfortunately, that T, there we go, hydrogen carbonate. Unfortunately, the old way is pretty prevalent, so you need to know that as well. Instead of saying hydrogen, we're going to replace hydrogen with bi. So we would call this bicarbonate. You might know this from baking soda. Baking soda is bicarbonate, sodium bicarbonate. So we have a sodium with that bicarbonate ion. So whenever you see a hydrogen, you're just going to stick hydrogen or bi in there. If you see either of those, you're going to be right. Okay. So name the following. All right. So go ahead and give these a name. Again, the first one always keeps its name. And normally I said, well, I'll do the first one. Normally I would say, oh, let's change the second one and add an IDE ending. If you have a polyatomic, notice this is not binary because we have 3 elements. If you have a polyatomic, it's just going to keep its name. So I would call this one sodium sulfite, because that's the SO3. SO4 would be sulfate. Sodium sulfite. Good. And the good news is sodium sulfite, the sodium is in group 1. Anything in group 1, 2, or 3, we don't have to add any weird lettering for it. All right. How about the next one? You give this one a go. Pause me, try to get through the rest of these. And actually, I'll let you do these from homework or for homework. I'll post them up there and then we'll talk about them. You might need a little bit of the naming system, but I think you'll be all right. Okay, so compounds containing metal ions with variable charge. Ionic compounds that contain a metal can be from one or more group, from more than one ion group. So we're going to use Roman numerals to kind of indicate those things. So for example, if we take a look at this first example, example 21, what would we call that? Well, FeCl2, immediately we want to name this without any other planning. We want to name this iron chloride. And this one would also be named iron chloride. Again, it's binary, so it gets the IDE ending. The problem with that is we don't actually know what those things, what charges those things have. We don't get any more information. They're 2 very different things. One has 2 chlorines, one has 3. They can't both have the name iron chloride. So in order to do that, what we will do instead is we're going to take the first one, write it out as iron, in parentheses, and I don't know why they still do this, but we're going to use Roman numerals to indicate what the charge of that iron is. Okay, and then chloride. So this is going to be the proper name. So we have to do a little test. And as from the previous thing, we know that chlorine has a -1 charge. There are 2 chlorines, so together they have a charge of -2. The overall thing is neutral. So if I follow this through, 1 gives me a 2- charge. What does this have to be in order to make this math true? What has to go in the parentheses? That's right, +2. So +2, and there's only 1 iron, so it's going to take the charge. The charge of the iron is +2. So this is going to be properly said. This is going to be iron 2 chloride. Okay, so iron 2 chloride is how you would say it. The other one, iron 3 chloride. And there we go. Okay, all right. Next up, copper oxide and copper oxide. Again, because these are in basically anything in the D block, anything in the center of the table, we're going to have a Roman numeral for. Again, the only things you do not have a Roman numeral for. So you get a Roman numeral for all but group 1, group 2, and group 3, or I guess that would be 13 on the more modern periodic tables. Okay. Aluminum is always 3+. Cadmium is 2+. Zinc is 2+. And silver is just +1. So anything other than that, those sets, we can essentially just ignore. Okay. Well, sorry, anything but though that set needs to have a Roman numeral with it. Okay. So copper, tin, mercury, and cadmium. Again, this, by the way, so this one right here, and I think that's why I put it in here. Cadmium 2 oxide. So cadmium 2+. Oxygen gets a 2- charge. Having that written is redundant. So that is actually the proper name, cadmium oxide, and 1 of each, cadmium oxide. Good. All right. So yeah, so that's how to do it. By the way, I hope you know Roman numerals. I guess I should do that quickly. Roman numerals. 1 equals I, 2, 3, 4, 5, 6, 7. I would never need anything past 7, right? Because it's impossible to have a +8 charge. 2, 3, 4, 5, 6, 7. Again, if you'll notice, the 5 and the 1 is in front of it. That's what gives me 4. So 5 minus 4, if it's in front of it, gives me 4. 5 with the 1 after it gives me 6. Okay. All right, good. So ionic hydrates. So ionic hydrates are, you're going to run into these occasionally. I'm trying to remember one. So if I have something like CoCl2 with 2 waters that come along with it. So essentially cobalt, we would have, oh, I can't capitalize that. Cobalt 2 chloride. Those 2 waters come with every cobalt. So it's important to say that those come together. So ionic hydrates are essentially a ionic compound with water attached. We could get into why they attach themselves, but it has to do with coordination and stuff. Ultimately, what it comes down to is there's always water attached. So for every 1 cobalt, you also have 2 waters attached for this example. So cobalt 2 chloride takes care of the first part. And the second part, the 2, we would say, basically say dihydrate. So I would know that there are 2 waters there. Okay. Sometimes we might say something like, let's see, zinc oxide monohydrate. But sometimes the mono is essentially ignored and we just call it zinc oxide hydrate. Anytime there's a hydrate, you assume there's one water there unless you see a different prefix. So sometimes it's used, sometimes it's not. It's not quite clear. More often than not, you're going to be asked for the name, or you're going to be provided the name. So if you see just hydrate, assume one. If you see any number of any prefix there, assume more. Okay. All right, good. So we've taken care of the metal ones. There's two options. If you have binary compounds, you have the two. You're going to name it. First one keeps its name, second one gets an IDE. If it's a metal, as it has been this whole time, you're going to check and see if it's in that group. Group 1, Group 2, Group 3, or Group 13, or zinc, aluminum, cadmium, or silver. If it's any of those, then it gets a Roman numeral. So ultimately what you do is, if it's a metal, quickly check the metal and see if it's in the D block. If it's in the D block and it's not the 4 that I mentioned, then you're good to go, and you don't need if it is in the D block, you will need Roman numeral. All right, so covalent compounds, these are nonmetals and nonmetals combined. So when we're binary, this is actually super easy. First of all, the least electronegative is written first, or the more electropositive. And so if fluorine is the most electronegative, we want to go is the one that's furthest from fluorine. So least electronegative, read that as furthest from fluorine. The one that's furthest from fluorine is the one that's going to be written first. Okay. The second one, again, same thing with any binary compound. That's why I always tell you to name them, regardless if there's a metal or not. If it's binary, it's going to get an IDE ending. And we're simply going to use these prefixes in front. So a prefix is to indicate the number of each. Okay. The one exception, though, is mono is never used for that first element. And weirdly enough, when a prefix ends in an A or an O, and the name of the second element begins with a vowel, we just ignore, we drop often. And notice that often is dropped. Okay, so it just comes from practice. I'm not going to hold you over the coals if you forget to drop the A or the O. I just want you to recognize it's there. So this first example here, CO2. Okay, so we see CO2. Again, I'm just going to write. In fact, I'm just going to do all of these. I'm going to just do these 3 examples right away. So first thing you do, first one keeps its name, second one gets its IDE ending. So do the first 3, just writing their names out. Leave space in between so you can actually add the prefixes. So carbon oxide, sulfur fluoride, hydrogen oxide. There we go. So there are the names of these things. Next up, I'm going to add prefixes. So there is 1 carbon. So I want to say monocarbon, and there's 2 oxygens, dioxide. Monocarbon dioxide. That is wrong because it's carbon dioxide, right? Again, anytime mono, if it's there, it's indicated that it's already present. So there's no need to add mono because we know carbon is already present. If there's no prefix, we just assume 1. So the next one, sulfur, there's 1 sulfur, so monosulfur, again, we ignore it. Fluoride, there is 6 hexafluoride. So sulfur hexafluoride. So 1 sulfur, 6 fluorides. The next one, hydrogen. Dihydrogen, 2, and then MON, monoxide. Notice that I did not add the additional O, okay, because it runs into a vowel. So O and A's, if they run into a vowel, we usually ignore it. Dihydrogen monoxide. By the way, if you're going to get rid of it, when in doubt, just say the word, like see if it makes sense. Dihydrogen monoxide, no, you need to get rid of the O, right? So monoxide, it's just going to roll right through. Again, I did not write mono for the first ones, but I do write mono for the second, which doesn't make a whole lot of sense because you would assume that there's just one anyway, but this is the life that we've chosen, right? All right, so and the good news is converting from a name back into a compound is easy. Nitrogen, dinitrogen, oxygen, trioxygen. So dinitrogen trioxide is right there. All right, carbon monoxide. Well, I just need 1 carbon because it's no prefix. Monoxide, 1 oxygen, done. So those are much easier to do that way around. All right. Next up, We're going to talk about acids. Acids also have a special naming system. So the first thing that you should really always do is, do I have an acid? And you recognize an acid because if you see the first thing written as hydrogen, you have an acid. If you see the group COOH, you have an acid. Okay, so, but what we're really going to focus on is if you see H first, you have an acid. All right. So the way that this is going to work, which is pretty simple, is first of all, binary acids. So HF, HF, HCl, BR. Notice that these are all in the, H2S. That's also an acid, H2S. All of these are acids. How do I recognize their acid? H is the first thing that I see. So it's pretty simple. We are going, so I would name this hydrogen monofluoride. That is the standard naming from above, right? That's the standard hydrogen monochloride, hydrogen monobromide, dihydrogen monosulfide, right? So that would be the proper binary name for these without monochloride, hydrogen monobromide, and the last one is dihydrogen monosulfide. That is the proper binary name that we would call these things. But then there is an acid naming scheme that we would use instead because we recognize them as an acid. And so the way that this looks is, I'm just going to write just a cheat sheet up here for it. Hydro, you're going to put the root in, and then you're going to have IC acid at the end. So let me just copy that actually. So we're going to write this 4 times below. I'm going to erase the root and the underline there, because we're just going to plug the root in. Again, this is supposed to be, feel very systematic, okay? So hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydrosulfic acid, okay? So it's not sulfuric, sulfic acid. So there we go. Those are the acid names for those. Again, hydro-IC acid with the root in between when you have a binary acid. We also have oxo acids or oxy acids. So again, we have the same thing, but this time we're going to recognize, so HCO3, let's say HSO4, HNO3. These are the ones you're going to see pretty regularly. H2SO4, I should say. And we can do HClO4. So normally we would call these, we were going to omit the hydrogen part of this. So normally we would call this hydrogen carbonate. So again, they would have their own name. So this would be, that should also be H2, my fault, H2. We would call this hydrogen carbonate. But of course, we're not going to do that, because what we really need to do is we need to name these with this system. So we're going to ignore writing the hydrogen part, and we're just going to start with the ion. Carbon 8. Oh, I guess I should probably change one of these. 1 second. Sorry about that. HClO4 minus, that's fine. Let's do, we're going to need one. There's a reason for this, and I'll see, you'll see in a second. Let me get rid of that one. Let me just get rid of these two. You can feel free to name those and add these if you want to. H2NO. Oh, there we go. HNO2. And Let's do HNO3. Those are better examples. Good. All right, so back to this. So carbonate happens to be the polyatomic, and we're always going to start with that. So if carbonate is the polyatomic, all we're simply going to do is take our polyatomic, and you're going to remove the ATE or the ITE ending, and you're going to replace it with, so any ATE gets replaced with IC acid, and any ITE gets replaced with OUS acid. Okay, so carbonate, we're going to simply mark it off. We're going to get rid of the ATE, and we're going to replace it with the ATE gets replaced with IC acid. So carbonic acid. Sorry about that. Yeah, better. HNO2. So HNO2 is nitrite. That turns into nitrous acid. HNO3 is nitrate. This gets turned into nitric acid. Okay, it sounds like a disease almost. Adic-itis. I call it adic-itis. It's the stupid way that I used to memorize it, but it's adic-itis. Okay, adic-itis. So that's it. So that's how you name those binary, or those any acid that contains a polyatomic in them. Okay, and there's your list of polyatomics. Good. All right, so we'll do a bunch of these in class, but that's our